Hello Math 2413 students, here's lesson 13, Integration by Substitution. Do you all recall the chain rule? The chain rule is the derivative rule for composite functions. It is arguably the most important topic in Calculus 1, and if you include all its variations, then we can argue that this is the most important topic in Calculus 1, 2, and 3 put together. One such variation is this one right here, integration by substitution. We aim to reverse the chain rule so that we can calculate antiderivatives of composite functions. Here's a motivating example. Stop the playback and try on your own. It's not too bad. So what did you get? There you go. You can separate the numerator, as you can see here, and then simplify term by term, like this, and consequently, you can integrate term by term. Alright, that was easy. How about the next example here? This time, you cannot separate the denominator. The answer looks like this, and try to work it out backward from the right hand side. By the way, you're going to need a chain rule here, so okay, I'll give the chain rule. Start from the right hand side, take the derivative of this composite function, and see if you get this integrand back, using the chain rule, of course. Indeed, we get this kind of computation. The derivative of log of x is 1 over x, so the derivative function for log function is the reciprocal function. And that's step 1 of the chain rule, the derivative of the outer function, green. And step 2, inside stay the same, red. And step 3, multiply the derivative of the inside, not back in, but outside like this, like a dangling chain. That's step 3, blue. And then the multiplication applies to the numerator, so you have u prime over u, so we get this computation. Of course, you can rewrite this integral kind of like this way as well, like this. Not there, here, 1, I mean, and then times 2x like this. And then take the derivative. Outer function, that's step 1, highlighted in green. And inside stay the same, red, that's step 2. And step 3, multiply the derivative of the inside, highlighted in blue, like that. So, you can calculate the derivative from the right hand side if you know the answer in advance. Now, what if you don't know the answer in advance? That's why you have to learn the integration by substitution. We will reverse the chain rules to establish that, and then we're going to go through some example problems here. But this can be a little bit rough for many students, so if you give up and just go over to the next video, it's going to be okay for most students. Still, it's not really recommended, so try to stay in and try to understand as much as possible, even if you end up throwing in the towel later. Okay, alright, here's the chain rule. Keep that as a reference. Now we're going to begin with this relation, the derivative-antiderivative relation. So, beginning with small f, that's the original function. In the derivative rule, we began with original function f and we took the derivatives to f prime, but that's for differential calculus. In integral calculus, we're going to begin with integrand f, that's the original function, and we want to find that antiderivative function, capital F. So the derivative of capital F is small f. Equivalently speaking, capital F is indefinite integral of small f. These two expressions are the same, equivalent. Equivalent modulo plus c, but let's ignore arbitrary constant plus c for the time being. In that case, these two are the same. Now let's apply the chain rule. Here, in the left-hand side, consider y as a composite function, like this. So y as y of x, then this capital F is going to become a composite function. And then by the chain rule, you're going to get something like this. Don't pay attention to this part and pay attention to this part only. And it's going to be better if I get this one as well. Okay, all right. So this part, the derivative of the outer function, green, inside stay the same, red, and the derivative of the inside doesn't go back in but outside here, like a dangling chain, blue. Step 1, step 2, step 3, they're all there, except for the change of characters. Instead of small f, we have capital F. Instead of g, we have y. That's it. We have g prime, so we have y prime. We have capital F prime, that's small f prime. So the chain rule here and this expression there, they are the same, exactly the same, except for the change of characters. Now, recall that we are beginning from the integrand, which is the derivative function of this capital F. So instead of this capital F prime, let's rewrite it as small f. And then let's rewrite this y prime of x as dy over dx notation. Let's rewrite this one, and let's ignore the middle part, and look at this. This is a chain rule, exactly the same. Let's keep this as a backup. Please check, they're the same. Y prime of x means dy over dx, yeah? And capital F prime, and is small f, so yes, they're the same. So this is a chain rule expression, and that corresponds to the left-hand side of this. Now let's re-express that like this on the right-hand side using the integral notation. If you do that, you're going to get this. So what do we have here? The derivative of capital F of y is the right-hand side. Here, the integral of the right-hand side is capital Y of x. So the derivative of capital F of y is the right-hand side. The capital F of y of x is the integral of the right-hand side. It's a derivative antiderivative relation. The derivative indefinite integral expression. So this is the same as chain rule, just written in the integral expression. Now let's do a bit of a simplification here. So what we're going to do here, let's keep this as a backup so I don't want to lose it. Okay, all right, and let's do a bit of a simplification. This dx down here, and then dx up there will cancel each other out. Now that we have just y, I wrote this y as if it's a variable instead of a function, then there's no reason to keep this y as y of x here either. So rewrite those as just y. And then what do you have? This expression and that expression are the same. Just an abbreviation. Instead of y of x, I just wrote it as y. And then instead of this dy over dx times dx, simplified into dx. This numerator denominator canceled out. This final expression is basically the reverse chain rule, but it has another aspect. What aspect am I talking about? That aspect is the substitution aspect. Compare this and that. One substitution is easy. Y is y of x. So that's easy. Second aspect, this thing here, dy of dx times dx, became dy, so it's a second substitution. Or equivalently, flip this to the other side, dx is dx over dy times dy. So if you multiply this in place of here and do simplification, they'll all cancel each other out because this and that are just reciprocal of each other, inverse of each other as a matter of fact. So we just get dy. So we get two substitutions inside, and then the derivative will give me simple integral. So from the chain rule, we get these two substitutions. Does it make sense? It probably will not make too much sense unless you do an example problem. So let's go back to this motivating example problem again, and let's work this out. Okay, this one here is the inside, and we want to substitute away this dx. How do we do that? Y is x squared plus 1. That's a substitution inside. Maybe I'll keep that over here. Okay, all right, that's what I just did. And then we want the derivative, dy over dx or dx over dy. We need the derivatives. So let's take the derivative from here. dy over dx, the derivative is 2x. It's just a derivative computation. dy is 2x dx. Just some algebra. Dx is therefore 1 over 2x dy. So we are ready, I guess. Put those in. Let's take a bit bigger font. The fractions, so bigger font will be helpful. So this x is y now. And instead of this dx, that's what you're going to multiply. It should be blue. Now, did you get simple integral? Apparently, this x and that x cancel each other out. And then we get 1 over 2y dy, or if you will, 1 over 2 times 1 over y. Oops. So that we get 1/2 and then log of y. Okay, we have correct antiderivative, but it's not the final answer yet because original problem is given in terms of x. So let's substitute one more time. Substitution number 3. Log of 1 plus x squared. You see, y is 1 plus x squared, or x squared plus 1, either way. So that completes the problem. I have the same thing here. Substitution number 1, inside of a composite function, derivative computations to get substitution number 2. You see, you earned red and also blue. Red inside and blue dx. Put those in, and the green part is not that important. I didn't specify green, I'll just use black. And then put those in, and then do your simplification. You ended up with much simpler integral. And then antiderivative computation is easy. And then original substitution, that completes the problem. So it all came from reversed chain rule. So this substitution and that substitution. But even if you forgot about all those reverse chain rule business, you can still make it work by those two substitutions. We'll do more exercises about those in next videos.